All right, I'll get started. We begin with a word of prayer. Dear Father, we thank you for this day again. I thank you for this class. Just ask you to bless our work today. Help us to glorify you, what we do, Lord. In your name I pray, Lord Jesus. Amen. So today we are talking about optimization. And so this takes a few days to really complete the story of optimization. Let me just kind of give you the big picture. We're thinking about, typically in here, a function of perhaps two or, well, first of all, if it's a function of one variable, we already know how to solve that, right? We learned that in Calculus 1, right? You guys remember first derivative test, second derivative test, the closed interval method, remember those guys? So that was the discussion of optimization in Calculus 1. So now we're thinking about, given, f equals to, say, f of x comma y, or f equals to f of x comma y comma z, how, where do the values of f take their max or minimum, right? So as we think about this question, obviously the immediate question is like, what's the context, right? Like, see if there's no context given, then the question has to be understood. Well, we're trying to find the maximum or minimum of the function at all possible points, right? In the domain. But you could be given these kinds of questions subject to some particular, domain, either in 2 or 3 dimensions. We'd like to be able to answer those questions. How do we find the maximum or the minimum of a function, even if it even exists, right? Maybe it doesn't even exist. How do we do this? What are the methods? And so the first method we're going to talk about, just to give you a sort of a bird's eye view of where we're going. Today I'm going to talk about the method of Lagrange multipliers, which allows us to answer the question of maximization subject to some constraint, right? So a constraint in 2 dimensions would be a curve. A constraint in 3 dimensions would be a surface. So we can solve the problem of f being largest subject to some constraint today. Then once we're done with that, then we're going to turn over the question to finding the maximum or the minimum of a function over some like open set or perhaps closed set, some sort of disk in 2 dimensions, kind of like an area, find the maximum on an area, or in 3 dimensions, find the maximum of the function over some volume, all right? And there what we're going to learn ultimately is that there's 2 possibilities. The possibilities are either that the function takes on its maximum on the interior of the set, right, at what are called critical points, we already defined those, or possibly the function takes its maximums or minimums on the edge of the set, which we call the boundary of the set. So in that second part of this story, the boundary, where perhaps we could think of as a constraint for the function, and we'll be able to use this method of Lagrange multipliers we're talking about today to find maximums and minimums on the boundary of an area or a volume for a given function. So this function in this discussion is usually called the objective function, because it's our objective to maximize or minimize this. All right. And so let me just tell you, here's the method of Lagrange multipliers. This is a theorem. If f attains maximum or minimum subject to the constraint g equals to a constant, then at such critical points, we have the gradient of f is equal to lambda times the gradient of g. And this lambda here is the so-called Lagrange multiplier. It's just a scalar. Right. Now, context here, I'm assuming that f is smooth, like you can take as many derivatives of it as you like. And I'm assuming that the constraint curve or surface here, likewise, is defined in terms of a smooth function. Yes, sir?
That's probably a lambda, right?
That's a lambda.
Oh, it is.
Yeah, I mean, it's a wrongly drawn lambda. My lambdas are backwards. So lambda is actually this. But I, for some reason, have hardwired in my brain that it's that. Some of you haven't noticed the difference. If you'd like me to correct this, I'm sorry, you'll need to go take a different section of Calculus 3. It's no longer something I can fix. It's been too long. Anyway, now understand, this is how it works in either 2 dimensions or 3 dimensions. All right? So let me show you an example of it before I show you the proof. All right? I'll show you an example how this works. So I like this example. This is a good example. Example 1. Suppose we're looking at f of x comma y equals to x squared plus 3y squared. And we want to find extrema of f on the unit circle. All right, there we go. That's the problem we're trying to solve here. So first order of business, what's my constraint? What's that? Pi to 2. Oh, no. 0 to 2 pi, yeah, sure. But how about g of xy equals to what? We'd like to write the unit circle as a level curve, right? So the level curve it is x squared plus y squared equals to 1, right? There we go. So that's my constraint function. Okay? Now, we use the method of Lagrange multipliers to try to find any extremum. So here we go. We're going to look at the gradient of f is equal to lambda times the gradient of g. All right? So the gradient of f is easy enough to figure out. That's 2x, 6y, right? What's the gradient of g? Two x, 2y, right? Now when we're solving a vector equation, it's a twofer in this case because it's a two-dimensional problem. We get 2 equations. And the 2 equations we have are, in particular, what are we up against here? 2x equals to, 2 lambda x, and also 6y is equal to 2 lambda y, right? These are the Lagrange multiplier equations that we'd like to solve. Now, the other thing that, I say at such over here in the theorem, at such critical points, right? So what does that imply? That you're solving this subject to what? G equals to a constant, right? It's never just the Lagrange multiplier equations. We also have our third equation, namely x squared plus y squared equals to 1. So this is the problem. We have to solve this system of equations. All right? So here's what I'll do. I will use factoring. Let me call this equation 1, 2, and 3. So equation 1 can be rewritten as 2x minus 2 lambda x equals to 0, which simply gives me x times 1 minus lambda is equal to 0, right? Do you guys agree?
Where did the 2 go?
Mm-hmm. Right? I mean, we can divide by 2. So what does this tell me? There are 2 cases, right? X is equal to 0, or what? Lambda is equal to 1. So choose your adventure. Let's look at this as case 1 and case 2, right? So if 1, then x is equal to 0 implies that 0 squared plus y squared is equal to what? 1. So that tells me that y is plus or minus 1.
If lambda was equal to 1, you plug in the second equation, you should get
I'm not doing lambda equal to 1. I'm doing case 1. So, yeah. So we find 0, 1, and 0, minus 1 as potential points for max min. They're possible extremal points for our objective function, right? So I have asked that laptops be shut during class, so please, unless you're looking at my notes, they really shouldn't be open right now. I've said this before, I'm saying it again now. 2. So number 2, so that's the 2 points, that's it. And by the way, in case 1, what would lambda be equal to? I mean, you can go back here. If you put y equals to 1, we get 6y is equal to 2 times lambda. So apparently lambda is equal to 3, right? If we put y equals to minus 1, I think lambda is still equal to 3. Does it matter, though? Like, not particularly. Lambda is just a device to find the answer. So we don't really care what lambda is. But it does happen to be 3 in case 1. Case 2, lambda is 1, right? And then what do we have? We have, 2x is equal to 2x, right, from equation 1, which isn't particularly useful, right? So that one doesn't really help us, does it? It's like, okay, great. Maybe we should look at equation 2, right? From 2, we get 6y is equal to 2y, which implies y equals to what? 0, right. And if y is equal to 0, then what do we get? But x squared plus y squared equals to 1 gives me then that x squared is equal to 1. Hence, x is plus or minus 1. So in summary, we obtain 1, 0, and also minus 1, 0 as possible points, points for extreme values Okay, so what's the story then? Which wins? Do you guys remember the closed set test in Calc 1? What did we do? We have a function on a closed interval. Remember we had to check the values of the function at the endpoints, and then the value of the function, any critical points inside. And then we make a list, and we pick the winners and losers from that, right? This is the same kind of thing. Sort of. It's a little bit, I say that because, well, we'll see the next example that, well, anyway. This presumes, as a precondition to the theorem, that f has a maximum and minimum. So the theorem doesn't give you the existence of the maximum and minimum. It may or may not actually have one. So the Lagrange multiplier equations can be deceiving. In this case, it's not, though. This actually will give us the max and min. I'll explain why here. So you guys work it out. So what's f of 0, 1? What's f of 0 minus 1? What's f of 1, 0? What's f of minus 1, 0? We can work out the four values. What are they? So we go 3, 3, and 1, 1. All right. There we go. So what this means, there's your max. And these, of course, are the minimum values. Now, there's a theorem that we can use to be sure, in this case, that those actually are, for certain, the maximum and minimum values of this function. And the theorem is this. Theorem. This is known as the extreme value theorem. A continuous function attains its minimum and maximum values when constrained to a compact set. Now, what's a compact set? Compact set means closed and bounded. So closed we talked about a little bit before. Closed simply means it's got no fuzzy edge. So closed means it contains its boundary, if you like. What does bounded mean? We haven't talked about that really. So it contains its boundary. No fuzzy edge. Bounded means that you can fits inside, a ball or disk. This is n equals 3. Here's n equals 2. Sufficiently large. So like, my constraint curve here is a circle. Does a circle fit inside a disk that's sufficiently big? Sure, take the disk of radius 2, right? The unit circle fits inside that. Is the unit circle closed? Yes, it's a closed set. It has it contains its boundary. I mean, the boundary of the unit circle is the unit circle, actually. But yes, a closed curve, as long as the curve doesn't if I had a curve like this, guys, if this was the curve, this curve would not be closed because it's missing the endpoints, right? And then this theorem would fall in that kind of context because it could be that you're reaching the maximum or the minimum at those endpoints, and that's how the theorem breaks down, right? But in my example 1, I can be sure that really is the maximum, that really is the minimum, because the unit circle is compact and the extreme value theorem applies. This is exactly the generalization of the closed set test from Calc 1. The n equals 1 version of this. All right, yep.
Could you show
That means that in particular I have the following equation. 1 is less than or equal to x squared plus 3y squared is less than or equal to 3 whenever x squared plus y squared is equal to 1. So, like, what does that mean graphically? Sure. I maybe can draw that. I can try. So z equals to, I can't always do this though. So this example is sufficiently simple that I can do it. But that is an elliptical paraboloid. So it's, I'm trying to think. Is it fat? Where's it fat? X goes to like plus or minus 1, right? In the, I'm thinking here. I'm trying to think of, if I set that equal to 1, what do I get? Set this equal to 1, I get what? I get like x equal to plus or minus 1, and I get y equals to plus or minus 1 over root 3. So that kind of helps me as I'm thinking about how to sketch this. So I'm 1 up, I go x plus or minus 1, right? And I go y plus or minus 1 over root 3. So it's like it's more narrow this way. So I don't know if I can draw this, but it's something like that, and it kind of goes up like that, right? Let me try it again over here. Ah! Something like that. And so we're constraining it to these inputs, like x squared plus y squared equals to 1 down here, right? Yeah. And as that lifts up to like a particular, I can't draw it, but it lifts up to, there's the values up here. So at 1, x equals to 1, this goes up to y equal to 0, so it's at 1, like here and here. And then apparently it's up, well, we have it over there, right? At 0, 1, and 0 minus 1 is up to 3, so it's like higher here and there. So I don't know, I can't draw it with anything, but something like that. So it's minimized that, the values of the constraint, the values of the objective function are smallest along the x-axis, and they go up to its biggest value along the y-axis. But yeah, I mean, I guess you can always think, if you want to think about it three-dimensionally, and I don't, then we're basically taking a particular subset of a graph of a function of two variables, and we're asking where is the graph tallest and shortest. If you want to think of it that way, we could. For a three-dimensional problem, I can't do this kind of picture. But there's a better picture, which involves the proof, basically. Now, before I get to the proof, though, I want to give you one more example. All right? This is a kind of silly example, but it's one we should do. And so my next example is, let us look at the objective function f of xy equals to x. All right? And we'll look at the constraint g of xy equals to x squared minus y squared equals to 1. Right? Let's try to apply the method of Lagrange multipliers to find maximum and minimums for f, okay? So we start out the same. Gradient of f is equal to lambda times the gradient of g. Gradient of f here is very silly, right? It's just what? 1, 0. And lambda here we have gradient g is what? 2x minus 2y. Right? So I'm up against the following equations. 1 is 2 lambda x, and 0 is equal to minus 2 lambda y. By the way, for this method to work, lambda must be non-zero. That will become apparent in the proof. When we look at the proof, you'll see why lambda pretty much has to be non-zero for the method to make sense. So since that's the case, this immediately tells me that y is equal to 0. If y is equal to 0, we have x squared minus 0 squared is equal to 1, which tells me x is plus or minus 1. We find only points what? We got 1, 0, and minus 1, 0, right? Great. So then check it out, right? F of 1, 0, what's that equal to? F of minus 1, 0, what's that equal to? 1 and minus 1. Okay, so which one's maximum and which one's minimum? 1 is maximum. And minus 1, max. Min, right? Of f of x comma y equals to x subject to x squared minus y squared equals to 1 is false. It is not true. What is this constraint we're looking at? Can we graph it? Right. So what is x squared minus y squared equals to 1? That's a what? That's a hyperbola, right? And if you put y equals to 0, you get x is plus or minus 1, right? And so the hyperbola is like this and like that. So the Lagrange multiplier method has deceived us if we listen to it. But notice the Lagrange multiplier method does have a warning at the start of the theorem. There's a pesky little word here, if matters, if it attains a max and min. So like the Lagrange multiplier method allows us to hunt for extrema, but we have to be careful. It can give us like false positives, right? Because obviously, you know, if you look at x, how big does x get on the hyperbola? As big as you want, because it goes on and on and on forever, right? We can make x as large as we want on this constraint. How small does x get? As small as we want, right? It's just a coincidence that, I mean, these points are special, right? That is the biggest, I mean, that is the smallest x gets. No, actually, it's the biggest x gets here, and it's the smallest that it gets here. Isn't that funny? Actually, this one, right, is actually a local minimum in some sense, right, subject to the constraint curve, and this is actually a local maximum subject to the constraint curve. It's very deceiving. So how can we be sure that the Lagrange multiplier method is helpful? Well, one way, if we have a compact, and why is this not compact, by the way? It's closed. That's true. This is a closed curve, but it's what?
It's not bounded because it extends off to infinity.
Right, it's not bounded. I cannot get a disk sufficiently big to encapsulate the whole hyperbola. It always escapes. Now, does that mean we can't use the Lagrange multiplier method unless things are compact? It doesn't mean that. It just means we have to use it with caution. We have to double check our answers and see if they're reasonable given the context of the problem. Okay, so there's your two starting examples. Let's look at the proof. So the proof of the method actually will be, it'll help inform us. It'll help us understand what just happened and why the method is what it is. So the proof starts with the assumption that suppose, f attains maximum or minimum at a point P, right? Let maximum at point P subject to the constraint G equals to a constant, all right? Let R be a mapping from, R to Rn such that R of 0 is equal to P, all right? And R of T lies on G equals to C. In other words, I want to let us consider So, we can draw. So this means what? This means, what I'm saying on here, we can make that into an equation. What does that mean? G of what? G of R of T has to be equal to what? Has to be equal to C, because we're saying it's a curve that lies on the surface, the constraint surface, or perhaps the constraint curve, all right? So that's point number one, right? And then, of course, from this, we get that the gradient of G at R of T, right, dotted with dr dt is equal to 0. Now, that's true for the whole path, right? Like if the path lies on this surface, then surely the tangent vector to the path has to be perpendicular to the normal to the surface everywhere where the path goes, right? It's not surprising. I'm going to do the three-dimensional picture. And so basically, here's what's going on. This is my G equals to a constant surface. Here's my path. Here's a particular point, right? And so at that point, you have nabla G at R of T. And of course, the tangent vector, like this, would be perpendicular. All right. That's generally true for each point on the path. But there's one point we're very interested in, which is the extremal point, right? The max-min point. Let's call that point P. All right? And notice I haven't pictured anything about the objective function yet, have I? But number two, if we let h of t equals to f of r of t, right? Then h of 0, by the way, is equal to f of r of 0, which is f of p. This is a min-max, min or a max, right? By assumption. But h is a function of one variable, right? So we know from calculus 1 if it's that has to be the maximum. 0 has to be either a maximum or a minimum for h, right? Think about this. If we're looking at the values of f, right, that are attained with respect to this curve that's on the surface of our constraint surface, and if that point is the place where f takes its maximum or minimum, then it must be also true that it's the maximum or minimum of f restricted to that particular subset near the point. What I'm trying to say is, if you think about all possible points close to that given point, if that point's a maximum or a minimum for f for all possible points close to that given point, in particular, it's a maximum or minimum subject to just the points like right there. So let me. So that means then that h prime of t, which is what? Gradient of f at r of t dotted with dr dt. Well, we know that h prime of 0 is equal to what? It's the gradient of f at the point P dotted with dr dt, right? That's equal to 0. This is always true for number 1, but in particular this is true for P, right? So we can see that this is also the case, that the gradient of g at the point P dotted with dr dt at 0 is equal to 0. This is at 0, right? So what does this show you? This shows us that the gradient of f is perpendicular to the velocity vector, and the gradient of g is perpendicular to the velocity vector, right? But how many different velocity vectors are we considering? I mean, was this a specific one? No, this was like an arbitrary path, right? So if you think about that, we've got all possible paths, right? All possible paths that go through that extremal point. And we have that, of course, the gradient of g at P points like that because it's the normal to the surface, but also the gradient of f is also perpendicular to all the velocity vectors, to all these different possible curves. What does that mean? Think about the geometry here. It must be, then, that the gradient of f points in the same direction as the gradient of g. How do we write that? So thus, the gradient of f is equal to lambda times the gradient of g. It has to be collinear. I mean, I don't know that it's the same direction. It could be anti-parallel, right? It could be the opposite direction, but it has to be some scalar multiple of g because they're mutually perpendicular to all possible tangent vectors, to all possible curves on the constraint surface. And that's why the method of Lagrange multipliers works. And it's also why I've erased it, but if you look at, let me put that picture back up. So like here, here's the hyperbola, right? X squared minus y squared equals to 1, right? What are the level curves of f? What do they look like? In this, my example 2, remember we had f of xy equals to x. So what do the level curves of x look like? They are vertical lines, right? X equal to a constant. And so where does the gradient of the objective function align with those level curves? Right? Which does it? I can't remember. I gotta think about this for a second. It always points this way, right? So, like here's some sample gradient f's, right? The only place where gradient of f and the gradient of g here so here's my g. So, there's just this one constraint curve, and if you look at the different, objective level curves, there's only one place where the gradient of f aligns with the gradient of g. Well, two places, right? This point right here, right? Right there, and this point right here. Those are the two places that we have the Lagrange multiplier equation satisfied. That's what we worked out, yeah.
So, the arrow has a, should that be gradient g? Is that gradient f?
Yes, it should. Thank you.
Okay, and then gradient f would be,
I knew something was wrong here. I couldn't put my finger on it.
would be the gradients.
I haven't pictured them, right? But like, of course, this would be gradient of f. Yeah. Anyway, let me not make my picture more busy than it already is. There's just these 2 points, right? Where the gradient of f and the gradient of g align. But that's what we're doing with the Lagrange multiplier algebra. We're trying to find where the gradient of the objective function aligns with the gradient of the constraint function. Yes, sir?
Do we have to draw something like this out and test it?
Sure. We could do that.
I mean, like, is that like one of the questions?
I mean, you're asking, so I mean, I think we could do that. I mean, why not? I give the students what they want, right? But no, I don't usually ask you guys to draw it because I don't want to grade that. You know, this is horrible. Anyway, I do have better pictures in the notes of this, right? I have like some computer-generated pictures of all these things.
So if that lines up with that, then why aren't...
Okay, so they do solve the Lagrange multiplier equations, but it's not a maximum or a minimum because x gets as big as you want if you continue on the hyperbola this way, and x gets as small, large and negative as you want if you go that way. So there is no maximum and minimum for x on the hyperbola.
Okay, so just because it solves the Lagrange doesn't mean that we...
Exactly. Yes. Like I was trying to say, there could be false positives. All right, let's look at another example, if I can. Let's see here. Yeah.
Is it the max level curve or it's just the max of the equation? Well, maybe that's a faulty question.
Well, we're asking what's the largest value for f subject to a point being on the hyperbola.
It's definitely not.
So another way, a much more complicated way to ask that question is, of all the possible level curves of f that intersect the hyperbola, which one of those level curves has the largest level or the smallest level? Because the objective function doesn't come with just one level curve, it comes with all its levels. We're trying to figure out which ones are the biggest and the smallest, you know? Let's look at a different example. Here's three-dimensional one. Suppose we have f of x, y, z equal to, well, x, y, z. Find extrema on the ellipsoid, x squared plus 2y squared plus 3z squared equals to 6. Good news, the ellipsoid is what? Can you fit the ellipsoid inside a ball sufficiently large? Sure, you can, right? You can encapsulate it inside a sufficiently large sphere, therefore it's bounded and it's closed. So this is a compact constraint, and as such, we will be able to find answers. If we could do the algebra, all right? There's always that, right? You guys remember the deal, like in Calculus 1, we have a theorem, any function that's continuous can be integrated, right? I mean, we have an area function for any continuous function. Does that mean you can find the antiderivative for any continuous function? It certainly does not, right? Like there's a very big difference between existence and whether or not you can calculate something. But I think we'll get through this one. Let's try it out. So here we have to look at, this is my constraint. This is the g, right? So we take the gradient of f is equal to lambda times the gradient of g, which is going to give us yz, xz, xy equals to lambda times the gradient of g, which in this case is 2x, 4y, 6z. So we're up against the following equations. We've got what? We've got yz is equal to 2x lambda we've got xz is equal to 4y lambda, and we've got xy is equal to 6z lambda. And what else do we have? Yeah, right. We still have the constraint equation itself. 4 equations, 4 unknowns, nonlinear. Remember this from college algebra? No, you don't, because we never did that there, because if we did, their brains would explode, right? But you're here, this is calculus 3, you can do it, right? But it is weird new algebra. So how do you handle weird new algebra? Use the basics, right? We hunt, but we hunt wisely. Like I did this factoring thing in the last example, right? The previous, okay, example 2 was so dumb we could just do it, but what should we do here? How to solve these? What do you want to do? Solve for y in the first one. What would you do with it then? What's that? Plug it in for y in the second one?
Equation and then like just a lot of work. Plug and chug.
Plug and chug. I want to believe. How about this? If I multiply these equations by oh, what if I divide the equations, right? What if I take if I divide them, the lambda's gone. We don't care about lambda, right? And like I said, lambda has to be positive or non-zero rather in order for the method to even be helpful, right? If lambda is 0, that means one of the gradients 0. So the logic of the search kind of breaks down there. Although admittedly, probably places where the gradient are 0 are also places where you should check. Right? If your objective function has a gradient 0 point on your constraint curve, probably you should just check that point, right? That's a critical point. Okay, so how about this? Let's look at 2 over 1. What's that give us? Yz over xz is equal to 2x lambda over 4y lambda, which simplifies simply. Oh, did I mess it up? Yeah, watch out for that. Don't let me do that. Thank you.
I think it's the same in that first part, so the xz over y and the 2 over 1.
Thank you. Fair enough. Yes, I am bound by my notation. All right, so we've got x over y is equal to? What's that? 2y over x? That's nice. But you know what's nicer? X squared is equal to 2y squared. Let's save that for later. I'll call that 1. Well, that's nice. How about, I don't know, maybe 3 over 2? What happens there? Oh, by the way, on a given day, I can get stuck on this algebra. Like, I don't just go willy-nilly into like Lagrange multiplier problems without having solutions nearby, unless I just want to waste students' time. I mean, I can do that. But hopefully not today. 3, you're like, that's debatable. Let's see here. 6, what do we got? We got xy divided by xz equals to 6z lambda divided by 4y lambda. The lambdas, they be canceling. And this gives me y over z is equal to 6z I guess we could write that as 3z over 2y, right? And that's nice, but you know what's nicer is that 2y squared is equal to 3z squared, right? Which, by the way, is equal to x squared. Oh, look at that. I think we have everything we need. Yes, sir? Mm-hmm. So, going back to the constraint equation, my g is x squared plus 2y squared plus 3z squared, but that's actually an x squared, another x squared, and 3x squared equals to 6, which tells me that x squared is equal to 2. So therefore x is plus or minus the square root of 2. And if x is plus or minus the square root of 2, what's the rest of it? We can look at those equations we found, right? What is y? Let's solve for y squared. Y squared is equal to what? Y squared is x squared over 2, right? So apparently, well, x squared that's 2 over 2, right? Which tells me that y is plus or minus 1. And z squared is x squared over 3, which is 2 over 3. So that tells me that z is like plus or minus the square root of 2 over 3. How many points do we have to check? It's okay, I'll get it.
9.
I heard 9?
Is that right?
It's a slight overestimate.
Yeah, you didn't hear it.
I didn't hear it.
6.
6. Now you got me guessing. Let's start out here. We've got. So we got to think about what is f of my x was what? Root 2. My y was 1. My z was root 2 over 3. Or we can have root 2, 1 minus root 2 over 3. Or we can have this one. 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 Or we can have that one.
You heard 9.
I'm pretty sure there are 8 here.
I can't count. You heard 8.
We have 3 things to assign, and we can do 2 for each choice, right? So it's 2 times 2 times 2, which is 8. Because they're independent, right? The plus, the minus in each thing. And so that's like, we got what? 2 over 3 minus 2 over 3. I meant square root of 3. I'm an idiot. Let's see here. Square root of 3, 2 over square root of 3. Minus 2 over square root of 3. 2 over the square root of 3. Minus 2 over the square root of 3. 2 over the square root of 3. 2 over the square root of 3. Minus 2 over the square root of 3. Okay, I think that we can pretty much see that 2 over the square root of 3 is maximum value of x, y, z attained where? At root 2, 1, root 2 over 3, root 2 minus 1 minus root 2 over 3, minus root 2 minus 1 root 2 over 3, and finally root 2, 1, and minus root 2 over 3. And number 2, minus 2 over root 3 is the minimum value of xyz attained on x squared plus 2y squared plus 3z squared equals 6. At let's see here, Pac-Man. Oh, that's not the Pac-Man, it's the Pac-Man. Oh, fine, I'll just write it. There's probably a more clever way of writing this answer, but I will just write it this way, as I'm not feeling particularly clever. There you go. So the maximum is attained at 4 points, the minimum is attained at the other 4 points, and there it is. Obviously this one's slightly more challenging than the other example we worked today, but nothing we can't do, right? So you guys, would you like to see another example of the 3-dimensional variety or the 2-dimensional variety? 3? All right. A rectangular box without a lid is made from 12 square feet of cardboard. Find the maximum volume of such a box. I'll repeat. A rectangular box without a lid is made from 12 square feet of cardboard. Find the maximum volume of such a box. You see, you did this in high school? Oh, that's good. Yeah, some of these things can be done if you exploit some symmetry or something. You can like boil it back down to like a problem involving a what's the word? Quadratic equation, and of course that you guys have complete ownership of in high school. Or even if you're just doing calculus, was it calculus in high school where you did it? Yeah. See there, it's also sometimes possible to like reduce it back to a 1 variable problem by an appropriate substitution, and then you can still do it. That's probably what happened, yeah. So, what example am I on here? 4? 4? All right, so we're going to let x, y, and z be the lengths of the box, right? So x, y, z. We've got box, no lid, 12 square feet of cardboard. We're trying to maximize the volume. So what dimension should we do? So the constraint, so the objective function is the volume, which is what? Right. So the V is like my F. So x, y, z.